So, shall we start? So, I think, the lights should go off. And this one, yeah. So okay. So, shall we start? Everybody's good? Great. Okay, so we ended up last session here. So one thing, some people ask me if we have, for the briefing, the project briefing, if we should have, coming in? If you should have a group submission or individual. It's a group submission, so every group has just one submission. So I don't know, but if I have not mentioned anywhere individual, it was wrong. So sorry for that. So we ended up here, which was about going very deep with neural networks, right? And then the point was that we talked about a bit of history where people started to just believe on deep neural networks, but then they saw that when you go very deep, then it starts to work to perform worse. And then we had this, we had this particular diagram here, the graphs, which showed us two different cases. So this was the proof of concept study by Microsoft in 2015, where people said, like, okay, we have 20-layer deep neural network, a convolutional neural network, and they wanted to just classify the ImageNet, and then they said, okay, the training error is just dropping as they are increasing the number of iterations or number of epochs, and then for 20 layers, it's working much better than the 56 layer. And we said that it cannot be overfitting because it's being seen both in the test result and in the training result, and this is not possible. When it's overfitting, then in the training result you should get better result, but for the test result you're going to get worse. Yeah. So this was the point where they concluded that going deep is not good, and we are somewhere here. So this is where people somehow got stuck. So VGG could go up to 19 layers, but when you go deeper, then it doesn't improve, and at some point it gets worse. And it was the same thing for GoogleNet. So they tried 22 layers. They could do better than what was the benchmark at that point, but they could not go any deeper. And the improvement was quite a tiny bit. So that was the conclusion at that point. And what is the reason? So the main reason, as I told you, people started to blame the idea of vanishing gradient. And what is vanishing gradient? So long story short, vanishing gradient means that when you go very, very deep, then once you start to backpropagate, when you want to compute the gradient with respect to early layers, it's going to get computed as the product of lots of things together, right? And if every single of them is a tiny number, or it's close to 1, but a tiny bit smaller than 1, then when you are very, very deep, this number is going to be very small. Meaning that when you want to update, your gradient is a very tiny bit, very small number, your weight is not getting really updated. So that layer is pretty much useless. And the deeper you go, the more of those useless layers you have. And later layers, maybe they do not capture the right thing that you want. Yeah? Maybe you wanted your very first convolutional layer to extract some features very properly because you need them later to do the classification. But when you go very deep, the first layer is pretty much not getting updated. So you are always extracting features in the very first layer with a bunch of random weights. And then that is not what you want, right? So this is the reason that they saw this behavior. And how we can understand it, my very close friend has a very nice sentence. He says that everything should be made simple as much as possible, but not simpler, okay? So this is why I am going to explain you in details, surprise, the vanishing gradient idea, but I'm not going to consider like the very complicated neural network. Yeah, the simplest neural network you can ever think of, just to give you the taste of what the vanishing gradient is. Okay, the idea of vanishing gradient. So let's just start with that one. So let's just consider a very simple example. So in this simple example, I'm considering a very dummy feed-forward neural network. So how dummy it could be? So it has a single scalar input. So one number as the input, yeah? And then it has L different hidden layers, yeah? And it has a single scalar output, yeah? So it is basically this guy. So I start from X as the input, and this guy goes to the next layer, goes to the next layer, and so on till the last layer, and then you get Y, whatever your output is, or theta. We started to call it theta. Yeah? So that's it. I mean, it's not a real neural network that you think of, but it is still theoretically a neural network, right? So it's going to look like this guy. So I assume that X starts. It gets multiplied with just a single weight, because I have just a single output for that neuron. I forget about the biases. I don't have any bias. So simply W1 gets multiplied with X. Then it passes through function F. And then whatever you get at the output, you multiply it with W2. Again, you activate it with function F again. And you keep on going till you get to the very last layer. You get theta. Clear? So it's a very deep nested version of your activation function F with different weights. Right? So now, if I want to just do a forward pass over this guy, what should I do? I'm going to start with my X, my input. I multiply it to the weight. I activate it. Then I get the guy here. Again, multiply it, activate it, the next guy, and so on till the very end. Right? So I can say my first Y, which is the first output, or the output of the very first neuron here. This guy is simply the activated version of W1 times the input, correct? And then I'm going to get this Y1. I'm going to pass it through the next layer, which means I multiply it with W2, and then I activate it again with function F. Clear? So I keep on going like this till the very last layer. So this is this guy, so the output of this last yellow guy here, which is going to be what I had from the last layer, previous layers, which is YL minus 1. I multiply it to the weight of that neuron, and then I just activate it. I get YL at the output. And the final thing is that I just multiply it to the weight of the output layer, activate it again with F, and this is my theta, right? So simple forward pass, just start with X, go ahead, correct? Now, let's go backward over this architecture. Let's see what's going to happen if we go backward. And what I want to do, I want to basically just go very back to the beginning, because to the first layer, because I want to compute the gradient, which here is a simple derivative, the derivative of the risk or loss with respect to W1. Okay? So my target weight now is W1, and I want to just go all the way back to the beginning of the neural network. Okay? So let's do it together. So let's just start with the very last layer. So what's going to happen here? I mean, where's the chalk? Okay, yeah. So what's going to happen here? This theta is coming to your loss, right? And then you have a true label Y. So you're going to compute this guy. This is going to be your R hat. So this is what I'm going to call it R hat. So this is R hat. And then I start to just move backward. Yeah? The first thing, as always, derivative of R hat with respect to output, right? And then it's going to be the derivative of R hat with respect to output theta, which you do know it. I mean, you just need to know the loss function. You can compute it, correct? So it's going to be L dot of theta and Y. That's it. Yeah. So you have that guy. This is what I'm showing as this theta dash. We used to do this in chapter 2. So this is my last derivative. And now the next thing is that I go backward and compute this guy is theta. Before that here, I mean, I had this WL plus 1. Okay, we have it there, yeah? And then here, at this point, I have YL, correct? This is my previous layer, right? And now, if I want to just compute, was it YL? Yeah, right, yeah, YL. So the next thing that I'm going to do, I'm going to get backward from theta to this guy, correct? So we used to do it another way. So when we had a messy neural network, we just get from theta first to ZL and then from ZL to YL, correct? But now, since everything is very simple, we can do it in one shot, right? So if I want to just compute now the gradient or the derivative of R hat with respect to YL, what should I do? Chain rule, correct. So, and if I want to write the chain rule, what is the variable that I'm going to start with? Theta, because I already know the derivative with respect to theta, correct? So I'm going to write it down dr hat with respect to theta, and then d theta with respect to YL, correct? And what about, I mean, this guy, I have it. What about this guy? What is theta? Theta is f of WL plus 1 times YL. This was theta. If I want to compute the derivative of theta with respect to YL, what is it? F dot, exactly, of WL plus 1 at YL times WL plus 1. Great. Yeah? So you have a weight, you have an activation derivative, right? So it's the same thing we had. Activation derivative, this is the activation backward, and this is the weight that you get in your backward move. Okay, so I'm going to write it down in this form. So YL derivative with respect to YL is going to be the derivative with respect to theta times derivative of theta with respect to YL, and then we just open it up, right? And now I replace everything. So I have the derivative of theta, I put it there, and then everything new, right? Next thing that I should do is what? Getting back to YL minus 1, correct? And I'm going to mimic, I'm going to repeat exactly the same thing, right? So I'm going to write it down if I want to just get to YL minus 1. I'm going to write it down as the derivative of R hat with respect to YL, the last thing that I had, times derivative of YL with respect to YL minus 1, which I have done a typo here again. Yeah? So you just noted it. Yeah? That blue YL should be YL minus 1, right? And then just replace it. So this is going to be YL dash. So this is what we computed from the last step. And this is again the same thing. The only difference is WL plus 1 is no WL, correct? Right? And now if I want to open it up, I can get YL dash from the line above. I repeat it. I substitute it in the line below, correct? So the derivative with respect to YL minus 1 is going to be the derivative with respect to theta, the very last guy, very last output, times the weights up to that point, times the derivative of my activation function, again up to that point. Correct? Everybody's clear? Great. So I can keep on going till I get into this point, right? Because I want to get into here to be able to compute the gradient with respect to W1, right? So if I want to go on, so I should go all the way back to the output of the first guy, the first neuron. And this means that I should be able to compute the gradient with respect to Y1. And that is, again, the gradient with respect to Y2 times the derivative of Y2 with respect to Y1. And now I'm going to just substitute this. I just go by induction backward. And then this is going to be of this form. You agree with me? So you have the derivative of your output. Then all of the weights till Y1 going to show up. All of the activation derivatives going to show up. So it's going to be the product from of L, yes, up to, of course, W2, because we are still here at the output of this guy. So from 2 to L plus 1, last layer, all of the weights, all of the activation derivatives. Correct? Right? OK, great. So I have this guy. I have the derivative with respect to Y1. And if I want to compute the derivative with respect to W1, simply I can start from Y1, right? because y1 is an immediate function of w1, correct? So I'm going to write it down in this form again. Again, chain rule. Derivative with respect to y1 times derivative of y1 with respect to w1, right? And that guy, I do have it. The first guy is that y1 dash, that weird product. And this other thing, again, you can simply write it down, right? So we could say that y1 is f of w1 times x. And now if I want to compute the derivative with respect to w1, derivative of y1 with respect to w1, I simply write it down f dot of w1x. So first I just take the derivative with respect to the argument, and then derivative of argument with respect to w1 is x. Yeah? So just instead of w1, I'm going to have x. Yeah? So nothing new, everything that we had in the previous chapters, right? So this is going to be x times this guy, and now I'm going to replace that, long product back here. Clear? Everybody's clear? So we just did it the messy way, but we backpropagated up to w1, right? And now we have the gradient of r hat with respect to w1. This is the thing that I am going to compute, and then I get this one, I multiply it with learning rate, and then I update my w1, correct? So if I want to update my w1, I am going to do it that way. So at the end of the day, one step of gradient descent is going to get w1 of the next iteration, t plus 1, to be the w1 of the current iteration minus eta times dr hat with respect to w1. So the thing that is going to update my first weight is that product, right? That guy is going to just sit here and update my weight, correct? Okay, so now if you look at this term, this is a kind of accumulation, right? Accumulation of lots of derivatives produced next to each other. And let's consider just two specific cases, right? So the first case that I want to consider is when my activation is a sigmoid function. When my activation is a sigmoid function, so do you remember what is the derivative of a sigmoid function? What was sigmoid itself? So sigma x is, I also forget it always. 1 over 1 plus e to power minus x, right? Okay, now if I want to compute the derivative, what is it? Yeah. So it's going to be this e to power, denominator has no derivative. So it's going to be e to power minus x, and then 1 plus e to power minus x squared, which you can write it down 1 minus sigma x times sigma x itself, right? You see it? So this power 2 is going to disappear. Then you write it down like this. This is sigma x itself, and that is 1 minus that guy, right? Now, sigma x sigmoid is between 0 and 1, right? 1 minus sigmoid, what about this? Again, 0 and 1. This product? Less than 1, definitely, right? So this sigmoid activation, when I have sigmoid activation, all of these f dots are smaller than 1, right? Correct? And let's assume that I started with some weights which are smaller than 1. Okay? And I'm at some iteration, all my weights are smaller than 1. Correct? So if this is the case, then the derivative is smaller than 1. Now what I can say every single argument in that product that you see here, all of those WL and all of those F dots, all of them are smaller than 1. It means that there exists one number A, one particular A, which is not 1, it is less than 1. It could be as close as you want to 1. 1 minus 10 to power minus 10, that's fine. But it's still smaller than 1. It's not 1, right? Correct? Okay. Now, if this is the case, now I can write down that derivative, this derivative of r hat with respect to w1. I would say every single entry in this product here is smaller than a, right? And if I exclude x and theta dash, there are going to be 2L plus 1 different terms, right? I mean, I have weight, I have the derivative of that guy, so this is going to show up twice, and I have one other guy here, right? So it's going to be 2L plus 1 different things, right? So I could say that this term, whatever that is smaller than theta dash x a to power 2L plus 1, correct? Everybody's fine? I don't know exactly what that is, but that is smaller than this one, right? And I told you a is smaller than 1. Now if I get a and take it to a very, very large exponent, what's going to happen? 0. Yeah? It doesn't matter how smaller than 1 it is. Always when you take it to a largest exponent, it's going to get very close to 0, right? So what I could say if I go very, very deep, like infinite number of layers, then that gradient is potentially 0, right? So the gradient is 0, meaning that when I'm updating, nothing going to happen here, meaning that my weight is going to be the same thing, right? The same thing as before. So this layer is not getting updated, right? So it doesn't matter how many iterations you go for, it's going to stop like that, right?
So why don't we use the idea of R prop where we only use the sign and we use a smart learning factor?
Yes, that's correct, but using a smart learning factor, I mean, it depends on your learning rate depends on the gradient. I mean, these guys here, right? These numbers here. All of those derivatives, correct?
We are just using the sign, not the numbers. The numbers.
Oh, just the sign. But I mean, you cannot even rely on that sign anymore. When that guy is very small, and you do know that this is a sample gradient, right? This is not the exact gradient at the end of the day. I mean, you have a bunch of data. X is one data point, and then Y is also the label, and you're going to do it for a batch of data, and then you average it out, right? But that average is a noisy version of the true gradient that we don't have access to, correct?
But we can still rely on the sign, right? Because
No, we cannot. I mean, if the amplitude is large enough, if it has enough amplitude in it, you would say that, okay, I mean, the error is negligible. So if it is, I don't know, 5, you might say, okay, maybe it's 4.9, maybe it's 5.1, that's fine. But when it is 0.0001, so was it really 0.001 or minus 0.001? And now you want to take the sign. The first one going to be plus 1, then the second one going to be minus 1, right? So you could simply just go totally wrong direction. So if you go towards that very tiny bit of gradient, it's going to be still better than going for only sign. I mean, of course, if you use rprop, you're going to benefit in some particular scenarios, but it's going to help you up to some point. Again, when you go very, very deep, it's going to even cause you harm. Yeah?
Doesn't this result mean that the rest doesn't depend on the last layer? On the first layer, sorry. So
Yes.
it doesn't matter, like it's not a problem, no?
It's a problem in practice because, as I told you, I mean, think about the first layer to be a convolutional layer, right? You get your image, you just pass it through the first layer. And what you do, I mean, the first layers are very important because they are going to extract you the features, right? So you need to have them very well trained. But what you see here, it doesn't matter. I mean, it's not like at some point it will start to be that. I mean, from the very beginning, it's not really getting updated, right? So always, the gradient being 0 is not because you are at a good point. The gradient being 0 is simply because you have gone so deep, right? And then from very beginning, your first layer is not going to get updated, right? So in practice, it means that whatever you learn in this neural network is that in the later layers, you learn how to perfectly extract things from those features. But in the early layers, you don't learn how to extract right features from your input. You're just extracting random features from your input, right? And then the good trained last layers are fed with a bunch of random things, which cannot really do the job that you're looking for, right? So you're just disconnecting the input to the output. Clear?
Is it like the profile of the loss would be like a plateau and then increases somewhere and you are like far, so you don't.
I don't get exactly what do you mean by the profile of the loss.
So like if you plot the loss as a function of W1.
W1, yeah.
Will it be like something like?
Yes, it's going to be. I'm going to talk about it shortly. So it's concentrated around 1, right? If all of your weights and derivatives are 1, then that product is not going to vanish, right? But if the moment it just deviates from 1, it starts to vanish or explode, right? And this is the issue, exactly. So your loss is going to be very high. Only when everything is perfectly around 1, it's going to just hit the right update, right? Yeah. So that's a good point. So this is what I wanted to say here. Yeah. So next slide. So moral of the story: when you go very, very deep, your weight, those gradients in the early layers are going to be very close to 0, and this is why we call it vanishing gradient. So through depth, the gradient is going to vanish. Okay. So this is one thing. The other case is that we have, you might say, okay, let's just consider the case where we don't have, or derivative is smaller than 1. Say, for example, we use ReLU and assume that the input is positive and everything there is positive, so we have no negative number there. And then this means that ReLU is simply a linear function in that case, and the derivative of that guy is simply 1, right? So derivative of ReLU is 1, so we're going to have 1 here everywhere, so they're going to disappear. And then say the weights are also larger than 1. They are not smaller than 1. Yeah? At least the majority of them are larger than 1. Okay? So what's going to happen? Say, for example, this is one number A again, and this A is a tiny bit more than 1, and you put your weight there, right? Everybody is there. So you know that everybody is larger than that A. Again, what you can say that this derivative, whatever that is, this is larger than, since all of those derivatives are 1, so they're gonna disappear, and then it's gonna be just L different weights showing up there, which is going to be A to power L, right? And A is tiny bit larger than 1. But again, if L is very, very large now, what's gonna happen? It's gonna explode, right? So it doesn't matter how larger than 1 it is, 1.0001, if you take it to power, 100, and so, it's going to explode, right? So at some point, it's going to get very large. So in that case, this gradient is going to explode, correct? And this is what we call the exploding gradient. Now, you might say why I initially just talked about vanishing gradient, because with the exploding gradient, we have at least something infinite, right? So we can clip it. This is something that people do. So exploding gradient is not as challenging as vanishing gradient. This is the first thing. And second thing is that in practice, most of the time, we see gradients vanishing, not exploding. Yeah? So in reinforcement learning problems, you could have that exploding as well, because your environment could behave quite random. But like in many supervised learning problems, the key issue is vanishing gradient. So here, the gradient is exploding. So the moral of the story is that when we go very deep in our neural network, we could either have vanishing gradient, meaning that the gradient of loss with respect to some weights, some layers, is going to get very close to 0, or we could have, what is this? Yeah, or we could have, why we don't have the, do I see it? Oh, sorry. Extremely small or large. Okay, I thought I have the two cases. So we could either have vanishing or exploding gradients, right? But as I told you, in practice, most of the time we see vanishing gradient, right? And then the key points in vanishing or exploding are the derivatives of the activation functions that you have, and also the weights, right? Because they are the one who are pushing you towards explosion or vanishing, right? Clear? So Now, this is one of the reasons that, for example, we prefer ReLU. I mean, beside lots of other reasons, ReLU, the good thing is that when it has a gradient, that is 1. Yeah? So, I mean, nowadays, vanishing gradient is not a big deal anymore. You're going to see it in few slides, but earlier people they practically experimentally saw that ReLU has gradient 1. This is exactly the nice spot that we are looking for, right? So this was one of the key points. And you might say why we used to just do batch normalization. Again, there are lots of reasons behind that, but one of the reasons was this, yeah? Because that batch normalization can help you avoid explosion of the gradient or vanishing of the gradient, right? So you don't get those weights crazy small or crazy large. Clear? So that's it. But you might wonder if we have any solution. So I am sorry, I think you asked me, okay. Oh, sorry, when you asked me, I just missed this line. So this is a standard terminology. So backpropagation accumulation concentrates at 0. So this is how people explain what you showed me in your profile, okay? So it means that when you just do the backpropagation, the number, you do it at the end of the day as a random thing, right? So everything is random, so those gradients that you compute are also random. But if you just sketch the histogram, the population of them, they're always going to be around 0. And the deeper you go, it's going to be a very, spikier kind of histogram. So they call it like concentration at 0.0. And what we would like to have, no concentration at 0, concentration at some other number, right? This is what we're looking for. Okay, so yeah. Now, you might wonder if there is any solution to that. So already I just told you 2 solutions. So one of them is to just use, better activation, ReLU, or you do batch normalization. But of course, you could imagine that those people who did 2015 study, they did already know about these things, right? So they have done it perfectly, but still it's not working. So the better solution, which came after that study, is what we call a skip connection. Yeah? And this is the base of what we have nowadays as residual networks. Yeah? So the next thing that we're going to talk about is the skip connection, or the idea of residual learning. But do you have any question up to this point? So did you get the idea of vanishing gradient? What is the problem? Just when you go very deep, everything could vanish, right? Great. So now what is the idea of residual learning? Yeah? So the idea is very simple. What it says that instead of learning a function, I mean, when we learn a function, or any classifier, for example, what we assume? We assume that there exists one, weird function, which gets one image, look at the numbers of the pixels, values of the pixels, and then it decides the class, right? So we are thinking of a function getting an input and then computing the output. And what we do with our neural network, we say, okay, we don't know exactly what that function is, but we put one neural network, which is a very good approximator of a function, and then we try to train it, just make it match to the data, hoping that it's going to extrapolate for everything else, right? So we are learning the function between input and output. Now, residual learning says why you are learning the function between input and output. Just learn the function that maps the input into the residual of the output and input. So what does it mean? It means that when you have a function like this, and you don't know what is inside this box, you're going to put one neural network here. You try to just approximate this f by training that function, right? But the residual learning tells you, okay, why you do that? I mean, you could potentially do this one instead, right? So you could say that I want to learn what is y minus x. Because if I do know what is that y minus x, if I know a function which gets x and gives me y minus x, then I can get that output added to x, which I have, and then that's going to be y, correct? You might tell me why this is going to work, but you're going to see that vanishing gradient is not going to happen here. So you're not going to have concentration around 0 anymore. Okay? So sounds a bit weird. You're going to see it and then everything gets clear. But at this point, did you get the idea of learning, residual learning? So here, I mean, what you do in this case, you have your data set which includes x and y, right? And then what you're going to do, you're going to learn this function f, correct? So you learn a function which gets x and give you y. And then you always take one neural network, put it here, and try to approximate that one. But residual learning tells you that why you do that. I mean, maybe you could do this as well, right? So if I give you x and y, you could say, OK, I'm going to make one neural network which gets x. And then this neural network, this is a neural network, it's going to give me at the output y minus x. Okay? Since I do have x as well, then I'm going to get this guy, add it up to this one, and then it's going to be y. At the end of the day, I want to get one x and get the corresponding y, right? So if I can get x and generate this y minus x, then of course I can compute y as well, right? So this guy is the residual. This is the residual. And this is the residual function. And I don't want to learn the function itself. I want to learn the residual. This is why I say residual learning, right? It's nothing new. I'm still learning a function, yeah? But that function is not the direct function, the forward function. This is a residual function. Clear? Now, you might tell me how it can make anything different as compared to the original one. So let's get back to that very simple example that we had, that deep one-dimensional neural network. And let's see what's going to happen when we do that. So what does it mean when we do a residual learning? It means that I have x, and then I'm going to pass it over all of these deep layers. And then at the very end, I am going to get this x, and then I just add it up to the output of my very last layer. Okay? Now, here, everything is as before. So I hope that I have, I have a clean board. Okay? So everything is as before. Where is the chalk? Oh. The only thing that is going to change here, I mean, what about the output of the first neuron? Is it different from before? No, it's the same thing. I'm going to give x. X gets multiplied with w1, then pass it through function f, and then I get the first output, right? What about the output of the second neuron? It's the same thing. The only thing that is going to change is the output, theta, right? So theta is now, I mean, I call the last output of this, I mean, the output of the last yellow neuron, I called it YL, right? So we use, in the previous case, we just wrote it down f of WL plus 1 times YL, right? That was it, correct? But now, when I want to compute theta, I have one extra sum, and that addition comes from input, right? Which is not x itself, it's W1 times x, right? So I assume just in my example, I assume that I multiplied with W and then add it to x. Okay? I can do it. I mean, I can change it, write it down x however I want, but I consider for this example this one. Clear? So everybody got the idea? So everything as before, the only thing that is different now is how I compute the output, right? Okay. So forward pass, everything as before. The only difference is this guy, right? Theta is now the YL plus 1 that I have. YL plus 1 is what we had before. So YL plus 1 is this guy. What we had before. Before this YL plus 1 was exactly theta. Now I'm going to add W1x to it, and then this is going to be my theta, right? Here? So this is going to be the forward pass. So I start from x, I compute theta, I have theta, I can compute loss, and now I want to go backward, right? I remember somebody told you that he's not going to go backward anymore last session, right? You remember him? I mean, this is not considered backward pass, right? This is very simple. Yeah? Okay, so yeah, I'm not going to expand it, trust me. Okay, so just this simple example. So now I want to just go backward, and I start again from the derivative with respect to output, right? Now, before I start going backward, do you think anything would change? If I get from theta to the output of the last neuron here, the red neuron, here what I want to get here, it is exactly the same thing as before, yeah, right? Because I want to get from theta to YL plus 1. And I don't care about the addition from input, right? And then when I want to get from this red one to yellow one is exactly the same thing, right? Everything when I'm moving backward is the same. The only point that it's going to change is exactly here, where I'm going to get the branch out, right? So just let's look at it, for example. If I just start with theta, if I do know the gradient with respect to theta, the first thing that I can do, I can go for YL plus 1. I don't care about x, right? I just care about the next thing that I need to move backward, right? And that is YL plus 1. So YL plus 1, when I write it down, it's going to be exactly the gradient with respect to theta, right? Because the partial derivative of YL plus 1 with respect to theta, or theta with respect to YL plus 1, that is 1, simply, right? Correct? Everybody sees that? Gradient with respect to YL plus 1 is gradient with respect to theta times derivative of theta with respect to YL plus 1. So derivative of theta with respect to YL plus 1. Look at this guy. What is it? 1 plus 0. It's 1 plus 0. 1 plus 0, exactly. That is not a function of YL plus 1, right? So when you take the partial derivative of theta with respect to YL plus 1, it's going to be 1, correct? So this is going to be exactly theta dash, right? And you are here, then everything is as before. So if I want to get from YL plus 1 to YL, I'm going to do exactly the same thing, right? And I'm going to keep going so on. Each time that I go one layer backward, I get one extra weight, one extra derivative of the activation, multiply with my expression, and I can keep on going till I get exactly to the output of the very first one. Nothing changed, right? It's exactly the same thing as before, up to that point, right? Correct? So derivative with respect to y1 is exactly the same thing that we had before. This is that theta dash times that long product, correct? But now, here is the trick. If I want to get now, at this point, this was the point where we computed the gradient with respect to W1, right? So if I want to compute the gradient with respect to W1, what should I do? Look at that let's look at that one and see how we can write that gradient or derivative. The derivative of r hat with respect to W1. I want to compute it, right? If I want to compute it, what are things in this neural network that are function of W1? Of course, y1 is a function of W1, right? Because y1 is f of W1 times x, correct? Am I right? Great. The summation is also an immediate function of W1, right? So I can say that theta, which is YL plus 1 plus W1x, that guy is also a direct function of W1, right? Now, if I want to compute this guy, what does chain rule tell me? I should write it down. I can't start with y1, so I can write it down d of r hat with respect to y1 times d of y1 with respect to w1. But should I stop here? No, because I have another function. So I'm going to write it down d of r hat with respect to theta times d of theta with respect to w1. Correct? And now I can stop because there is nothing else in this neural network that is a direct function of W1. Correct? Everybody got the idea? Right? Okay. So I can just use what I computed in the backward pass, and I just replace it here. Right? So the first term is exactly the thing. I mean, derivative with respect to y1. This is the one which we computed in the previous slide. d of y1 with respect to d of w1, we computed it before, right? We know this function. It's going to be w1 times derivative of f, right? F dot, right? This is derivative. This is this term. What about, I mean, this guy, d of r hat with respect to theta. Do we have it? Yes, we started with that guy, right? This is theta dash, yeah? This is the derivative with respect to the loss, with respect to the output, sorry. Yeah? What about this guy? d of theta with respect to w1. What is it? This is going to be x, right? Okay, so what I'm going to have, I'm going to have x here replacing from that term. I have this term. This is exactly the thing that we had before. Sorry, I think when I was explaining, I did a mistake. So where is the, what did I do with the chunk? Here. So yeah, derivative of this guy, I mean, I think you all see it, but d of y1 with respect to w1, it is f dot of w1x times x, of course, because we are taking derivative with w1. So I'm going to replace them here, and then I do have both of these guys, right? So theta dash is the thing that I started with. What about y1 dash? I computed it in terms of theta dash, right? So it was theta dash multiplied with all of those derivatives, correct? So I'm going to write it down here. So theta dash going to stay here times x. I factor it out because this y1 also includes theta dash, correct? y1 dash is simply theta dash times that weird long product, right? So it's going to be this one, and then this is the product that I had, and here I have plus 1, correct? Now, plus 1 is this term, theta dash. I'm factoring it out, right? Now, if I go very, very deep, where does it concentrate? 1, right? It's not 0 anymore, correct? So I don't have any problem that my gradient is vanishing anymore, correct? So the thing that is going to happen is that you're going to have still this accumulation, which could vanish, but you have one term coming from the skip connection, and that term is not going to vanish. Yeah? And this is going to carry information from the input towards very output, right? Now, this is the idea. I mean, it sounds very simple, but it somehow helps. Okay? So this was the one which people started to use when they saw that behavior I showed you. And I mean, after some dealing with it a bit, I mean, after some design, it started to work. Now, if I want to talk about skip connection in general, I mean, if you have a neural network, which is a feed-forward neural network, starting from an input going towards the output, you can get any layer, the output of any layer, and then you can take it to a couple of layers next, and then you can add it up to output of that layer. Yeah? Then the thing that you are doing a skip connection, and you are making one residual unit. Because that unit between this skip connection is not going to learn the forward function anymore. It's going to learn the the residual function, right? So this is what we call it a residual unit, and that is the skip connection idea. So say, for example, ZL is the output of one, for example, convolutional layer, or maybe a fully connected layer, and YL is the activated version of that one. So any kind of layer you could have, then when you want to talk about a skip connection with depth S, then you're going to have ZL, and then you're going to just look at S layers before, so you're going to get the output of that layer, and then you take it in, and then you add it up with the output of your own layer, and then you activate. Okay? So this is going to be the skip connection. Okay? Now, here is a couple of things. First thing, what is this guy W here? I might need it Do you see why I might need it? Is there any reason for YL minus S and ZL to be of the same dimension? No, right? Is there any reason for layer 2 to be of the same dimension of layer 4? No. You could use a kind of convolution in between. You could just increase the width of your fully connected layer, and the dimension of the output is going to change. Then you need a transform to make them of the same dimension so that you can add them up, right? So that W is simply that guy. So it is something that gets multiplied. So I put a general multiplication now here, right? I don't know why. I mean, it depends on the kind of object I have in that layer. If it is a tensor with weird number of dimensions, then I probably need to do a kind of tensor-wise product. Yeah, I don't know, right? But I can always use one tensor, just do a bit of linear mixture in it, and then I change the dimension, right? So this is what this W is going to do for me. And the second thing that you might ask me, why I took the activated output, and then I take it with the skip connection. Yeah? There's no reason for that. So instead of Y, you could put there Z. Yeah? So you could do it before activation, you could do it after activation. Doesn't matter, really. Okay? In practice, people try, see which one works better. Okay? And the last thing, you might say, okay, why you added it up and then you did the activation? Again, there is no must. Yeah? You could do the activation and then you add it up. Again, you need to try it. Okay? Clear? So there is no reason for these things. I mean, in practice, people use different versions of this idea, but all of them does the same thing. It gets the output of one layer, either activated or non-activated, take it to another layer, make adjustment for dimensions, and then they add it up with the output of that layer. Clear? Everybody's clear? So you got the idea? You have a question? Okay. When I think it's because of that one. Oh, sorry. No, the other microphones are, I don't know, maybe it's because of other microphones are off. Yeah.
One more thing, you said we can time the W. So I'm looking at this page. Looking at this page.
Okay, yes.
A couple pages before.
Yes.
So
Here.
I was looking at the X, W1. I think
Okay.
you just said W1 can be times after the skip connection.
It could be, yes, it could be.
But I thought that was the key point. We have to time this W1 before the skip connection so that
if I want to compute the gradient with respect to W1, you're right. But if I care about the derivative with respect to X, it doesn't matter, right?
No, what I'm thinking is if I time W1 afterwards, so the skip connection, everything in the middle, the weights in the middle are the same as before.
Not necessarily. I mean, the weight that you saw in that slide, it could be the weight of this green one. So I have here W1. W1 times X is my Z, right? It is Z1, correct? And I got Z1. I can potentially multiply it with some new weight. I didn't do that here for you. But I can do it with a new weight, and I can learn that weight.
Yes, no, I'm saying the W2, W3, and everything.
Yeah, everything in between is not changing, right? For them, everything is the same. Yeah, so we are, I mean, you're going to see it in a couple of slides. We don't do just that kind of very long skip connection. We're going to make short skip connections, and then we make larger skip connection if we need.
Yes, but the point is everything in the middle, between two connections, everything in the middle, the weights are is not changing. So that before we pass into the skip connection, we need the residual part, which basically y minus x. We pass it in, and the weights in the middle will calculate, what transformation do we do to the y minus x then we add it to the x, we get the y.
Yes, I mean, this guy is exactly the one which computes y minus x. You're right.
Yes.
And then you get the output y minus x, but as the input to this guy, you give x itself, right? X is the function that goes inside,
Yes,
and then you compute y minus x, and then you add up x to it.
yeah.
Huh?
Okay, I was thinking something wrong. If we apply W1 after the skip connection, it will still be some sort of transform. It will be y minus x before we give everything.
Yeah, sure. Still, it would be, yes, yeah.
Okay,
Yeah,
yeah.
yeah. Okay, so everybody got the idea of skip connection, right? Yeah. So this weight W here that you're taking to just make the adjustment in the dimension, you could potentially learn it as well. Okay? So it could be a bunch of learnable parameters that you are going to train, compute the gradient, update them, and then it's going to work. Yeah? But in practice, we even don't do that. Okay? So we just take the addition. Okay? So now, yeah, maybe we could have 5 minutes break, and then I'm going to just show you the real residual network that we have. Okay? So shall we go on? Okay, so yeah. So now, one thing I think your friend also asked offline. So when you are doing residual learning, when you are using a residual network, so you usually are supposed to do batch normalization, because all of those, addition and stuff like that you're doing, so they need to be of the same level, right? So if you don't do it on the same level, if you don't get, if your input is hugely different from your output, then that addition is not going to impact that much, right? So because of that, when you just marry skip connection with batch normalization, then it's going to work really fine, okay? This is going to work. Like, you can really go deep. You're going to see it. Now, this is the one which people started to work with when the idea of residual networks came out. So this is the initial proposal. So what is the proposal? It says that you're not going to just get one skip connection all through your network, because obviously it's going to help you to just get whatever is in the first layer, for example, but anything in between is still going through a deep neural network, which is feed-forward, right? And then that one is not going to help, right? So the idea is that we make modules, right? And this is what we call it the residual unit. So it means that you make a few layers, then you do a skip connection, you look at it as one unit now, and then you stick them together to make a very deep residual network. Okay? So the unit that they initially started with was this guy. So what they said like we have input X, and this X is going to pass through some weight layer, so it could be a convolutional layer, or it could be a feed-forward layer, fully connected layer. And then you do the activation, then again you do a weight layer, so again one convolution, or a fully connected layer. And then at the output, you're going to get your input and you add it up here. And in the very first proposal, which we still do it most of the time, they do not do any sort of weighting here, so they assume that the weight is simply 1. And also they got the input, which is after activation, because that X is coming from output of another layer, right? So X is after activation, and then they give it here before the next activation, right? So this is consistent with what I showed you in the previous slides, okay? But you could play around with that, as I told you. Then they called it a residual unit. So this is the building block. And they started to stick it together to make it deep, okay? Now, a typical residual unit, it usually consists of two, but you can go deeper, so you can have larger number of layers within that one. And in the initial proposal, as I told you, you're going to get your input. This X is basically the output of one activated layer, potentially. And then you multiply it with some weight. You add it up to the whole process. So the whole process from this input to the very output before that addition of the skip connection, it's shown here YF. So you're going to add it up here. Then you do the activation. You get the output. And then once you get the output, you're going to pass it through another unit, right? And you keep on going like this. So you could, as I said, you could in general put 1W here. But in the initial proposal, they just put it to be 1. And then they did one experiment, extensive numerical experiment. They saw that when they do batch normalization, the W up, if you put W as well, when you optimize it, it's going to be close to I, identity matrix. Okay? Meaning that, forgetting about training that and putting it that particular one to be 1, that weight to be 1 is completely fine. Clear? As long as you have the same dimension, of course. I mean, if you don't have the same dimension, then you need to change the dimension. Okay? Now, what we do usually in practice is that we have a residual unit, and we keep the input-output dimension the same. So this is what, for example, you do in assignment 3. But then after that, you're going to get maybe 1 or 2 layers that you change the dimension. Then again, this has no skip connection. And after that, you put another residual unit. Okay? That's going to be easier for implementation. But of course, you can change dimensions, so just to be clear. Now, this was the idea proposed by Microsoft, and in the paper you can click here. This is one of the most well-known architectures, and nowadays kind of benchmark for many visualization tasks, and it's quite now robust against vanishing gradient. Okay, so you can simply go, you're going to see it, you can simply go hundreds of layers. That's easy now. Okay? Now, before we go forward, we go further, let us just do one forward-backward pass. Sorry, but I'm not going to do that kind of weird forward-backward pass. It's just a very simple, cheating one. So, how we are going to do that? So, say we start with some input x, and then, for example, x could be a tensor in general with c different channels. Then this x is going to, for example, get passed over one convolutional layer. So in your residual unit, if you remember, this was the residual unit, right? So this is your x that's coming in. So you have first one convolutional layer. So now this is z1, and then z1 is going to get activated, right? So this is your whatever activation is. And then you get another one, same as that one. So z1 is here, y1 is after activation. So you're going to do the convolution, and then since I want to keep the number of, the dimension the same, I'm going to use exactly the same number of filters as I have channels, so that the number of channels in the input and output are the same. Then I'm going to get z1. z1 is of the same dimension. I'm going to activate it. Then I'm going to do again another convolution. With the same number of channels, I just want to keep the dimension the same, right? And then once I have done this, then z2 is the output of this guy. And then when I want to compute the very output y, I am going to just first add x to z2 and then activate it. Clear? Everything works fine, right? Now, you might think that if we want to go backwards, it's going to be very weird. But it's not. It's basically, it's exactly the same thing as we did in the very dummy example. So say I want to go backward. And if I want to go backward, I do have the gradient with respect to y, right? Correct? So let me show it here. So maybe I just rotate this guy. So if I want to go backward, I have x here, and then I get the first convolution. Then I have z1. I do f, the activation. And then I get y1, and then again another convolution. Now I get z2, and now I get this guy. I bring it here, I add it up, and now I get the activation after activation f. I'm going to get the output y, right? And now if I want to move backward, I have the gradient with respect to y. You can simply come here, right? Can you? You can, right? So that one is nothing. It's just an activation. Now, if I want to get from this one to this one, should I do anything? No. Nothing happens. From the derivative point of view, if I have the derivative, say call it z. If I have the gradient with respect to z, then the gradient with respect to z2 is going to be the same thing as gradient with respect to z. So I'm actually here, right? And now, from this point, if I want to move backward, what should I do? Another convolution, right? So you do know how to get here. How can I get here? Entry vice product. How can I get here? Another convolution. The only point that this skip connection is going to show up in your backward pass is going to be when you want to compute the gradient with respect to the very input, right? Beside that, everything is the same, correct? Yeah? So if I start from z2, which is this guy, so I can start from this point. If I have gradient of y, then the gradient of z2 is simply just going backward over an activation. Then I want to get to y1. It means this guy. I just need to do one convolution. Then from y1 to z1 is activation again. The only thing is when I want to compute the gradient with respect to x. I know if I want to compute the gradient with respect to x, same thing as we did here. I mean, we just looked at the guys who are depending on x, on W1, right? Same thing going to go here. So I'm going to look at the guys who are depending on x. So Z1 depends on x because this is the immediate output of the first convolution fed by x. And very last guy, y, is going to be also a function of x, correct? So I can simply do that. So I can say I have the gradient with respect to z1, the first immediate function, times a kind of product, I don't care, gradient of that thing, z1, with respect to x. This is chain rule, right? Plus gradient with respect to y, which is the very output, times, again, another product, I don't know, I don't care for the moment, and then the gradient of y with respect to x. Clear? Now, if you do a bit of math, you're going to see, I mean, you just need to concentrate and you're going to see that this is entry-wise product. And this product you don't really need to compute. Because this is, again, I mean, you get from z1 back to x. What is it if this guy was not here? What was it? Convolution. Again, you're going to do a convolution. Okay? So at the end of the day, you're going to have one convolution plus one entry-wise product. So the backward propagation, is exactly the same thing as you had in the convolution. If you replace every layer with a fully connected, is exactly the same thing as we had in chapter 2. Whenever you see this skip connection coming out, you're going to have one extra term, and that is the term which avoids vanishing gradient. Clear? Everybody's clear? Great. So, yep. Residual networks are actually those who are very deep, and then you just take these residual units and put them next to each other. Then they are going to do very well. They can go very deep. As I told you, you can have simply 154 different layers. The depth could be 154, and they are still working fine. No vanishing gradient, no problem. Okay? So you can go deeper here because you have a skip connection. The key factor here, the key point in this residual networks is the skip connection that lets you go very deep. And you could have different kinds of layers, so you can put in between convolution, pooling, I don't know, fully connected, whatever you want. But the typical one is the one which I showed you in the figure. And everything as before you can again use. So you can use dropout. Batch normalization is strongly suggested to be used when you are doing a skip connection. And also you can just use any sort of optimizer on your architecture. It's going to work. I mean, you see that back propagation is nothing, right? It's exactly the same thing as before. So usually people call this residual networks, in short, ResNet. So ResNet is the thing that usually nowadays you see in the papers, like more recent papers when they want to just get a benchmark, they usually use ResNet. And you have the pre-trained version on PyTorch and Torch Vision. So you can access it, just run. I mean, for ImageNet, it has been trained. You can just do a bit of extra fine-tuning to just get into a better version for your own purpose. So now here, this is the thing that in that 2000, when Microsoft people reported that ResNet architecture, they proposed it. This is the thing, one of the experiments they did. And what they did here, so what you see here, the first guy is 34-layer ResNet. And you see that this guy is a real ResNet, right? Because you start from your input, and then you do a bit of change in the dimension, and then you're going to do one residual unit, two residual units, and you keep on going till the very output. And then at the output, you're going to do your classification. Just pass it through a fully connected layer and softmax. Okay? So they did it this one, and this has 34 different layers with lots of skip connections in between. Same thing copied here below, but they don't have any skip connection. This is the plain convolutional neural network. And this guy is, I think, VGG 19, I guess. yeah, the most dense one, but one of the VGG benchmarks. Yeah, again, this guy has no skip connection. This is one of the things. I mean, at that point of the time, this guy was known to be the best proposal. Yeah, because it was the winner of the ImageNet challenge last year. So now, what they have seen. I mean, this is the thing that you get by VGG. And now here, what you see is error, meaning that you go lower, it's better, right? And then this is the top one error. So when this was one of the metrics they had. So when they test it multiple times, and then they take the largest error, which is like the worst case scenario, right? And then here is the top 5. So you just go for multiple tests, but you don't take the worst one, you just come multiple down, right? So just let's look at this last column, okay? They both describe the same thing. So this one is giving you, I mean, that was VGG16, okay? So VGG16, which was the winner of the last year, it's giving 9.33% error when it's doing classification. If you do it with plane 34, then you are getting 10.0.2. You've gone deeper, but you got higher error. It shouldn't happen, right? This is because of vanishing gradient, right? But then, if you go for ResNet, I mean, they have different designs, A, B, C, but when you go with any of those designs, you always get smaller as compared to both plane 1 and VGG, okay? So what is happening here is that ResNet is letting you to go deeper, and as you go deeper, you are getting better. Okay? And this was what they also showed in the same figure that we had before, right? So this is the case where you have plain neural network. So you went from 18 layers to 34 layers, and you see this is training error, and it's going higher. Yeah? It shouldn't be the case, right? You're going deeper, but your training is getting worse, and it's simply because of vanishing gradient. But if you replace it with ResNet, now when you get from 18 layers to 34 layers, now you are getting better, and it makes sense now, right? You're going deeper, you are getting better model, and this model is getting trained better. Clear? It's in the order of 10 to the power 4, everything here. So it's 500,000. But it's iteration, it's not epoch. I mean, you should do some.
Why we can see some very hard decrease in some moments?
Yeah, because your network is getting saturated. I mean, if you go very, very, very complex at the end of the day, I mean, you have a certain complexity in your function. So you are not expecting that you just get crazy better, but you shouldn't get worse, right? So it's always the behavior. Like you go deeper, initially you get a very good boost, but at some point you start to saturate, but it's not going to be like fixed. Yeah, it shouldn't go down at least, right?
Yeah, and then after we have a very...
Oh, you are talking about the curve. This is a kind of behavior because you are somehow, if you do a couple of experiments, you're going to get feeling about this. You also see the same thing with accuracy because, it depends on the learning rate that you have tuned, but if you tune it like properly, then you get into a local optimum, and then at some point you can jump out of it, and then you go to other one. So you start here, then you suddenly jump, then you suddenly jump, and then you stay there. Yeah.
I thought that was because of we reduced the learning rate so that we get even closer.
Yeah. They have done the scheduling, but why they suddenly jump out when they do the scheduling is because they were stuck to one, local optimum, and then they did the scheduling right, so they didn't stay in that point, and then they got out of it immediately, right?
I wonder how they do that because usually we very hard to jump out of the local.
Yes, those who wrote this were quite professional, so they spent all of their life on doing that. But nowadays, you can't really do it with predefined tools in PyTorch. Okay. At that point, there was no PyTorch, I guess, yeah. Yeah, there was no PyTorch. 2015, yeah. Okay. So, any question on that? Everybody's clear? And once again, to just annoy you for the last time, this thing is the training curve, and it cannot be overfitting, right? Yeah, I said it 1,000 times, but this is important, yeah? Because this is the key that we saw that behavior and we went after ResNet, right? Great. Okay, so as I told you, ResNet could simply get deeper and deeper. So we have ResNet 152, and then as you can see, this error could now decrease constantly. So you get smaller and smaller error as you go deeper, right? So you don't see any worse result when you go deeper anymore. And this is simply because of skip connection. But ResNet is not the only one. So as you can see, ResNet the next year won the ImageNet challenge. And as you can see here, I mean, we started with shallow network, just 8 layer, 9. I mean, we were slightly increasing the layers, the depth, because we really couldn't go that deep because of vanishing gradient. But when they could resolve that issue, then boom, it just went 152 layers, right? A huge number of layers. They could train it. Backpropagation was still working. Yeah? Backpropagation always worked. Yeah. Yes. It's just about computation. I mean, we two things. One thing is that we are just, I mean, daily getting developed in terms of computation and in storage. This is one thing obvious. And the second thing is that nowadays, since people believe on these things working, backpropagation working, they are designing specific processors which do the job that is needed for backpropagation, right? At that time, people were not doing. So it was a general purpose processor, and then you just use it for your own task, which is going to work. I mean, if you add up CPU, it's going to work, but it's not as efficient as the things that we have nowadays, right? No. But this one, you can easily, I mean, train it on your laptop. It doesn't matter what your laptop is. It doesn't get more than a day or two. Definitely, definitely. Even if your implementation is very basic CPU, you're going to do it, I'm pretty sure. I mean, you should start with good weights which are available, but then you can do it. OK. Any questions? No question. Great. So there are other architectures which are using residual networks, so residual units or skip connection. So some of them are using short skip connection as ResNet. So what is short skip connection? You always have a short connection from input to output. And you just, when you want to go deeper, you just put those blocks next to each other. But you can go for other kind of skip connection. So this is, for example, UNet. Probably some of you have seen it, heard of it. It's, again, one of the good ones that we do lots of classification with it. And what does it do? It just starts from the input, and then it goes in a form of a U to the output. And it has both short connections. So when you get at the bottom of somewhere in the middle of the model, you get short connections. But as you get towards the edges, you get longer skip connections as well, right? And that one could be more efficient when you have more serious problem where, again, vanishing gradient is showing up, even though you have short skip connections. And DenseNet is one of the crazy ones, 200-something layers. And then you just try to do a skip connection as much as you could, right? And then you have both, again, short skip connections and long skip connections. Okay?
Yeah. About the unit, I am thinking that skip connections solve the gradient vanishing problem between two connections, so that if there is a short connection over here, why do we need a bigger one over here?
Yeah, but if you think about anything before this skip connection, if you don't do any of those long skip connections, anyone before this central skip connection is still seeing that gradient vanishing, right? Vanishing gradient.
Okay, so that why don't we just do a small skip connection right here and then right here?
Yeah, that was one idea, but which was ResNet basically. Oh. So you have lots of small ones. But then they tried this. They said, like, if we take information from like both near layers and far away layers, it's going to help. I mean, at the end of the day, all of things that we say here are justification. What is happening in practice, we cannot really go into it. We don't know what is happening in very, very details. We just have some intuitive idea that what is happening, right? But we just try them out. So we just do experiments. Sometimes it might be one architecture is theoretically or intuitively better than the other one, but in practice it works worse because simply the algorithms that we have developed up to this point, they are not very well training that architecture. Yeah? There are some challenge in between that we don't see. Like the vanishing gradient is the simple one, but many people didn't see it earlier days. Right? At some point they started. Yes, yes. Yeah. Usually the progress in this field is always like that. So people come with some intuitive idea, they try it out, and then out of some numerical result they get some feeling, and then some people later try to justify it with some concrete math. No. Okay. So, yeah, few notes on implementation, because at this point that we are, you have knowledge of some, benchmark, namely this ResNet idea. And if you want to do it, for example, you can do it in PyTorch, and you can simply use what is the pre-trained model. And what is the pre-trained model? Pre-trained model means that somebody someday got this ResNet, they know that it works fine, so they just got the ImageNet data set, and they trained the model for that data set. Okay? Then they ended up with a bunch of weights. They saved those weights. And they put it in a library in PyTorch. And whenever you want to start using ResNet, you just load those weights, and you initiate your neural network with those weights. Meaning that if you give ImageNet image to this neural network, without needing to train it again, it's going to do the right classification for you. This is what we call it pre-trained. Some people did this training before. Yeah? And pre-trained is not a unique thing. I mean, maybe 10 people do training. They end up with different weights, and they all save it. So there are different versions of a same model pre-trained. Okay? So the one which is saved in PyTorch usually for most of the models is the one which is consistent with ImageNet classification. And the reason is simply because of the ImageNet challenge. Okay? What does it mean? It means that the input layer is a tensor 224 times 224, number of pixels, with 3 channels. Because the input of the ImageNet is 224 times 224 pixel image RGB. Okay? Since this is the input in ImageNet, the model that they had pre-trained is getting such input, right? And the output is 1,000 dimension because ImageNet has 1,000 classes, right? Now, it doesn't mean that if you want to use this model for another application, you cannot. If you want to do it, you can simply just get this model, do a bit of modification at the input and output, and then it's gonna, if I just, instead of that 1,000 dimensional layer here, if instead of that one, I just remove the output layer of that pre-trained model and replace it with one layer, one fully connected layer with 10 outputs, then I can use it potentially for 10 class classification, right? If I change the input layer instead of 224 times 224 3 channels into 32 by 32 3 channels, then I can use this for example, CFAR classification, correct? So I can load that model. I can just play with the input and output, and then I can use it for my own task, right? Now, if you, for example, go in PyTorch and then you just, from Torch Vision, you import these models, and then you just write models dot, and then you press tab, you're going to see lots of them. You see, all of them are available. And not only the model is there, you see the weights are there as well. So these are the pre-trained weights. And when you load your model, you can load your pre-trained weight. Okay? If you use anything else like TensorFlow or any other thing, they exist there as well. You even can download it from their web page usually. So this is one sample example. For example, ResNet 50, if I want to load the pre-trained weights. So the thing that I'm going to do, I'm going in Torch Vision, I'm going to import the ResNet 50 itself. I'm going to import the weights. And then I can just take ResNet 50, and then I just load it with pre-trained weights. So I'm going to go inside the weights. This is the version 1 of the weights. Okay, some people just trained the first version and they saved it. Then some people came after. They said like we did even a better training, and then they just gave version 2. Or I mean I don't know. I mean I just prepared these slides a couple of last year, so I don't know. Probably there are more weights right now. I don't know if there are any people still working on that, but you always can load them in that form. Yeah, clear? Yeah.
Yeah, I found that what is the ResNet and something like that. I couldn't understand ResNet weight.
What is? I mean, ResNet at the end of the day is a bunch of convolutional layers and skip connection and everything, and they have weights, right?
Yeah.
So if you want to train it, what you're gonna do? You're gonna just get this ResNet. You just generate it. I mean, if you don't want to do that, you're going to just put the convolutional layer next to each other. You write the code. You have the whole model, right? But then you need to train it, correct? So you're going to start with some bunch of random weights, and then you're going to train it. But some people have already done this and saved those weights.
For our model?
For ResNet, yes. When you want to do ImageNet classification. ImageNet classification. Might be some people have done it for CFAR. I'm pretty sure you can find the pre-trained weights for CFAR as well. But typically what you find in most of the toolboxes is for ImageNet, simply because of ImageNet challenge.
And for example, when we use this way, we are in a halfway and something like
Yes. When you want to do CFAR, I'm going to say it in the next slide. But yeah, that is the idea of transfer learning, yes. So yeah, so if you don't initiate your weight with some pre-trained weights, this is when you don't put any weights, so you start your model purely random, then you do need to do the whole training by your own. But you can use the weights from the other people, and then you start from that point, right? Even if you want to do ImageNet classification, you can start from that one, and then you train it for multiple extra epochs. Hopefully it's going to get better, right? So that's the idea of pre-train. You can also, load it from Torch Hub, but Torch Vision is the typical one. I mean, earlier days, some people used to use the Torch Hub. The last thing that I want to tell you is about this question that your friend also asked. So I told you that you have the pre-trained one. Typically, they are for ImageNet, but you might say I want to use that model for CFAR classification, right? Meaning that my input is 32 by 32, 3-channel. The output is 10 classes, right? So what I'm going to do, I'm going to load the pre-trained one. I'm going to get rid of that input layer. I'm going to change it to a 32 by 32 layer, 3 channels. And then the output, I'm going to remove the last output layer. I just put the layer with 10 outputs, right? Now, this is a model which gets CFAR and does the classification. But if I use those pre-trained weights, does it do the right job for CFAR? Do you think that it does the right job for CFAR? Not necessarily, right? Because it was trained for ImageNet. I'm not giving ImageNet, right? I'm giving CFAR. I actually changed the input and output layer. So you might say, what is the point in using those pre-trained model if we are not dealing with the right data set? The point here is that of course, it's not going to perform best, but the point is that if you start from that pre-trained model, which you have modified, and you start going for training, this is going to converge much faster as compared to the case where you start from fully random weights. And you might say, why this is happening? I mean, CFAR is just classifying 10 different objects. ImageNet is doing it for 1,000, right? At the end of the day, cat is in both of them, right? And they need to just look at the eyes of the cat to find out this is a cat. So that pre-trained model that you got from ImageNet has some idea about how it can extract the features. And then when you start from that point, of course, you are halfway done, right? You just need to fine-tune it, right? This is one places that we do the fine-tuning. You just want to tune it again, right? Or some people, earlier days, they used to say this kind of property, the idea of transfer learning. So it means that the model that you have trained for one particular data set, the learning in that environment could be simply transferred to another environment with much less efforts as you start totally in that environment and you try to do the training. So this is the idea of transfer learning. Transfer learning is not simply what I told you today. It has much more details, but for the thing you need it in this course, that's enough. Okay? So now you can simply just load a pre-trained model. You can just modify the input-output, and then you can do the training for your own thing, your own task, and it's going to work fine. I mean, if you try it for like with these guys for CFAR 10, you're going to see it easily. Okay? So I think that was the last slide. Okay? So, oh, we have 7 minutes. What are we going to do? Shall we start another? Just joking. Sorry. So we're gonna start on Tuesday with RNN, okay? And I might do it a bit faster next week, so I don't want to have too much materials for the first week of December, okay? Okay. And one thing I'm gonna let you know about the final presentation session, okay? So I'm still looking for different ways to do it, but when we finalize, when I get the final idea, I'm going to let you know, probably in 1 or 2 weeks, and I'll let you know what the place. So we need still to reserve it.
Does it also go for another week of December, or just?
Yeah, I think we're going to have it in the second week of December. Yes. Yeah. Okay. Okay. So great. See you on Tuesday.